Awesome. Yeah. Okay. All right. Okay, so let's get started. All right, so welcome back, everybody. This is the very first seminar of this year's OSU ALT seminar series. We are very happy and very excited to have Professor Aidan Ozgan from UCLA to give us a talk today. The title of the talk is Deep Learning Enabled Computational Microscopy and Diffractive Imaging. So let me give a brief introduction of Professor Ozgan. And Dr. Ozgan is the Chancellor's Professor at UCLA. And he is also the HHMI professor with the Howard Hughes Medical Institute. He is associate director of this California Nanosystem Institute and has been selected as the fellow of the National Academy of Invention. And holds more than 80 issues granted patents in many domains. Dr. Ozgan is the author and co-author of more than 1,000 peer-reviewed publications and has been awarded many superb awards that anyone dream of as a scholar. For example, he has been awarded as the Peace Award by NSF, which is one of the most prestigious awards in the engineering domain, and he is the International Commission for Optical ICO Prize. He won that prize, and also he has won the SPIE Early Career Achievement Award, Army Young Investigator Award, NIH Director's New Inventor Award, and many, many more. I can't even count them. So he's one of the very renowned scholars in computational imaging and mobile sensing, particularly in the domain of healthcare application, which we call mobile health. And he's one of the very early scholars who is, developing deep learning-based technologies and apply these technology for computational imaging and mobile health research. So, without further ado, let's welcome Dr. Ozgan for the talk.
Thank you. So, can you all hear me fine?
Yep.
All right, wonderful. Well, thanks for having me. It's a great pleasure to connect to you over Zoom and share some of the work that we do on deep learning enabled computational microscopy and imaging. So my lab is interested in 3 different themes, one of which is computational microscopy, how to enhance microscopic imaging or features that you get out of a microscopic image using deep learning. And I'll spend perhaps half of my talk on this domain. Another area in my lab has been point-of-care diagnostics, sensing, mobile sensing, and how to create, for example, inexpensive, cost-effective, field-portable devices that can give us the same sensitivity, same specificity, the same resolution that you expect from their lab-grade counterparts. Kind of democratize advanced measurement science, and that's been something that I've been doing for about 2 decades at UCLA. Not shown here, a third area in my lab is on diffractive computing using light-matter interactions programmed using deep learning. I'll touch on that toward the very end of my talk if I have time. So for the last several years, my lab has been interested at this intersection of deep learning and imaging microscopy, but from the specific perspective of image reconstructions, image transformations. I'm not very much interested in segmentation or classification of images or tumor margin detection, et cetera, for different biomedical applications, but really, how can we use the framework of deep neural networks for reconstructing images, transforming images from one mode of imaging to another. For all of this framework of solving inverse problems in computational imaging, arguably there is one very exciting and attractive feature of deep neural networks, and that is once they're trained, they're non-iterative and rapid. This is on the contrary to a lot of the existing inverse solutions before deep learning. They were iterative, they were slow, they took a while for their final result. Deep learning changed that, giving us extremely rapid input-output relationships, solving inverse problems of various different kinds. The first application of deep learning to enhance a microscope or the images of a microscope came actually from our lab in 2017, which is already an issued patent. It was actually using bright field microscopy to showcase how we can improve the resolution and depth of field of microscopy, performing spatial frequency extrapolation, taking a low numerical aperture, large field of view image, and mimicking high resolution, high numerical aperture, but an extended depth of field image of the specimen. Soon after that, we've applied it to reconstruct holograms, to take holographic microscopy or quantitative phase imaging into another domain where neural networks were mimicking what physical reconstruction methods based on the Maxwell's equation were doing. So it's kind of giving you another framework for rapid phase retrieval, rapid microscopy. Some other examples are shown here. This is arguably my favorite. You can take a smartphone-based microscope that has resolution limitations, color aberrations of different kinds, and establish a transformation using a neural network through pairs of image data coming from an inexpensive field portable microscope versus a diffraction-limited benchtop state-of-the-art microscope. So you can actually take inexpensive images in the field and rapidly convert them into high resolution and state-of-the-art diffraction-limited imaging systems. This was actually the baseline, the first step of success for using deep neural networks to approximate physical forward models and provide solutions to inverse imaging problems. One common theme in all of these has been the physical forward model was known. So we exactly knew what the network was approximating because we were doing these kinds of image reconstructions using different kinds of physical models that were inverted. So this is kind of like the obvious utilization of a neural network as a universal function approximator to solve inverse imaging problems with strictly non-physical forward models. But soon after that, we realized as a community that there is a much bigger opportunity. Arguably, the biggest impact for the use of deep neural networks in computational microscopy has been to approximate unknown functions through image data. So think of a transformation from the perspective of a microscopic image of a specimen. We do not know if that function exists, how to model that function. Can I do those kinds of transformations on microscopic images of specimen? Well, you can even consider a function that you do not understand or you do not know a physical forward model to approximate that. And through supervised learning and image data, approximating these unknown functions became possible. So, well, this is a little bit abstract, and I'm starting to lose some of my audience, I'm pretty sure. Let me give you a little bit more context to this function. Let's assume that this function in this specific example is going to take fluorescence microscopic images of specimen and transform them into bright field microscopic contrast. So fluorescence to bright field transformation, we don't have a forward model for that. It's very difficult. We don't have the proper understanding across different specimens how to relate fluorescence to bright field. That's two different apple to orange type of a transformation. We don't have an understanding of that kind of physical forward model. As if this was not complicated enough, we'll be looking at label-free samples at the input, and I want them to look like labeled under bright field contrast. So that means this function is even more complicated because it also looks for some labeling transformation to be implemented from label-free to labeled, autofluorescence to bright field. And that's why it's autofluorescence, because there's no exogenous fluorophore here. Well, this is so peculiar. This is so kind of a specific cherry-pick transformation that I'm describing to you. Yes, but if I could transform this, perform this kind of a transformation, I could change the way that we do histology and staining in histology biopsies. So for the last 2 centuries approximately, we're taking biopsies from patients and we're staining them with different kinds of chemicals, just because we do not know how to implement this function through a microscope. Well, a biopsy sample is cut into very thin sections for them to be inspected under a microscope. If you don't use any chemicals, chromophores, different kinds of dyes, the microstructure of this thin section, let's say 3-4 microns thick, it doesn't have any contrast under a bright field microscope. And that's the exact same reason why for the last literally 2 centuries approximately, we've created different kinds of stains so that under a microscope, the texture of tissue looks with some contrast, revealing cellular, subcellular features, etc., enough for a diagnostician to write the report on the patient. Well, that function that I just described, this F function, if I could implement or I could learn that, I could stop the workflow here and instead of chemical staining, perform virtual staining using an AI through supervised learning, mimicking the function of this entire chemical staining and bright field contrast. That means without any exogenous fluorophores, external labeling, take the label-free specimen that is thin sectioned on a glass slide. We take autofluorescence microscopic images, beautiful diffraction limited microscopy coming from a digital scanner. But at the same time, to learn this function, I sent the same samples to the histology lab for the ground truth to come with bright field contrast after labeling. And this deep neural network is learning this transformation F function that I just described to be able to do virtual staining. The framework behind this is actually a conditioned generative adversarial network, where 2 different networks are fighting. These are convolutional networks, are fighting with each other. The inputs are diffraction limited autofluorescence images, no exogenous fluorescence. It's completely native to tissue, thin sections. This generator is the artist. It's painting the microstructure of tissue, converting fluorescence into bright field contrast, label-free specimen into labeled equivalent. The discriminator is actually the critique. It's trying to understand which image is chemically stained, traditional workflow, and which one is virtually stained using AI. It's not just a game theoretic approach between the two. Actually, there is some structural loss term that makes the generator not hallucinate and be faithful to the micro and nanostructure of the tissue. That's very important because at the end of the day, we want to make sure generator creates the actual specimen's labeled version, not hallucinate any features. And once we're done with the training through supervised learning, we take the generator and that is fixed. And everything that I'll show you in the next several slides, they're coming from generators that are tissue stain specific. They're trained, fixed, and we're showing new patient specimen never seen before. It's literally a blind testing result. This actually works for a number of different types of stains. The most commonly performed stain is H&E. This stain is perhaps 95% of all human tissue staining done today. It takes approximately 2 hours for a histotechnologist to create these kinds of beautiful H&E images. What we need is an autofluorescence signature microscopic image of the specimen label-free. It's contrast enhanced for your eye here. So this is just contrast enhancement just to show you that, hey, these are beautiful diffraction limited images. You don't need that contrast enhancement. It's just for the humans to kind of appreciate the beauty of the microstructure there. A network blindly infers this in a matter of less than a minute, rapidly revealing images that match beautifully well what comes out of histology, saving approximately 2 hours of his technologist's time staining it. It doesn't only work for the basic stain H&E, it also works for what we call special stains. These are more exotic stains that are lower in volume, but they're more expensive. For example, this is kidney specimen. Jones Silver stain, it's a special stain that is approximately 10 times more expensive at UCLA Health to perform. It takes 3 hours, tedious stain to perform. This is what comes out of histology lab. If these technologies is available to work on your specimen, you get this after 3 hours of staining. Again, autofluorescence channel here is shown of label-free tissue, fixed tissue, and this is virtual staining results. Beautiful match to what comes out of histology. Some other examples are shown here from a third type of stain, Mace's trichome. It's also a special stain that is more expensive, and that's more expensive, and at the same time 10 times more expensive, and at the same time tedious to perform. And you're shown here liver and lung tissue specimen, nicely matching what comes out of histology, again with label-free contrast coming from autofluorescence microscopy. Arguably, the most difficult, most challenging staining that some of our biopsies are going through is immunohistochemical staining of tissue, IHC in short. So this is actually a molecularly specific stain. It looks for antibody-antigen reactions, and this one takes 24 hours for ground truth, which means you're looking for an overnight incubation and tedious steps. Literally, if you're the first patient in the line, it will take approximately 24 hours to stain your specimen with immunohistochemical staining features. Here, you're looking at HER2 staining. It's basically a key biomarker for breast cancer patients, which is very important for determining the target of therapy. For example, this is a breast cancer patient that doesn't express HER2 as much. This is HER2 0, they call it. This is HER2 3+, score, meaning that all this brown is coming from HER2 expression at the cell membrane. So you can achieve immunohistochemical staining using virtual labeling of label-free tissue by using, in this case, a panel of autofluorescence channels. We use different off-the-shelf filters. Again, there's no exogenous fluorescence here. Do not confuse these filters with fluorophores. These are just filters. We're looking at endogenous native fluorescence coming from tissue at different channels, giving you these synthetic contrasts from label-free specimen, which is converted beautifully well to a HER2 stain in this case, nicely matching what comes out of histology lab after 24 hours of labeling. These were examples so far that I was giving left and right, virtually stained, histochemically stained clinical workflow, to show you that, hey, these are really nice matching in terms of structural similarity index, PSNR, in terms of color distances, you name it. We've quantified all of those engineering matrix. But on top of that, a very important matrix is what pathologists think of our images as opposed to the standard clinical set of images. And here I'm sharing with you some tables showing you that from the perspective of diagnosticians, in a blinded manner, a group of pathologists looking at quality of our images, like nuclear detail, cytoplasmic detail, extracellular fibrosis, without knowing which one is histochemically stained and which one is virtually stained, they gave lots of scores. These kinds of tables we created to show that there is statistically no significant difference between our images and their quality from the perspective of pathologists versus standard clinical histochemical staining workflow. In fact, we also gave them several cases for them to diagnose the patient and looked into their diagnosis achieved with our images versus standard histochemical staining to again show the same conclusion that there is no statistical significant difference in the diagnosis achieved using virtual staining compared with histochemical staining, showing you that it's not just beautiful looking microscopic images, but these are also preserving microscopic features that contain diagnostic elements of pathology. But it's not just an effort to make microscopy great again, right? So histology great again. No, it's actually more than that. It's transformative in a number of different ways. First, a very important advantage of virtual staining is we standardize the quality of staining. Look at these examples. These are most simple stain, H&E, the basic stain from UCLA Health, chemically performed. From run to run, you have a huge variation. And this is globally happening. If you look at H&E images from Asia, from Europe, from the Americas, etc., you will see these kinds of variations. This is bad for diagnosticians, but it's also bad for downstream machine learning. Deep neural networks, once they're trained and fixed, they're consistent. Consistency is good for diagnosticians. It's also great for downstream machine learning to process these kinds of images in a standardized way without getting lost into the style or color differences of different labs that are generating these images. This standardization is very, very important. Arguably, the biggest advantage of virtual staining is multiplexing and tissue preservation, which means from a single cross-section of label-free autofluorescence microscopic image, we can create a panel of stains. We can create H&E and some special stains that are frequently needed for different diagnostic cases. And these are nanoscopically registered for the first time. They're perfectly registered panel of stains coming from the same tissue, which means we save tissue and we create multiplex information channels for the diagnosticians. Today, it's done in a destructive way. If you need a panel of stains from a biopsy specimen, you cut different sections and stain them with different stains. That's why they don't match, because tissue is heterogeneous and 3D. That's why you're looking at different cross sections, which is bad. And more than that, you deplete tissue. A lot of secondary biopsies are required because staining, traditional staining, depletes and destroys tissue. If you ever wondered why you or a family member was called again for a secondary biopsy because of this destructive nature of clinical staining performed in histology labs, that would not be necessary with virtual staining because we do not touch the specimen. It's all from a single cross-section multiplex staining. So far, I've been talking about biopsy specimen and the application of virtual staining on biopsy samples. This framework also works for autopsy tissue. In fact, much better. There's a major problem with autopsy tissues, and that is severe autolysis due to delayed fixation of tissue makes staining very difficult, and in some cases completely fail, especially during COVID-19 pandemic, because of the large volumes of autopsy specimen that needed to be prepared. There was a huge delay. And what did that do? Well, tissue denatured, and it couldn't be stained. Look at, for example, this is a COVID autopsy specimen. This is my ground truth. The chemically stained H&E images. Nuclei are missing there. This is completely useless because tissue denatured and we could not perform state-of-the-art H&E there, and half of that autopsy was literally useless because of delayed fixation. Virtual staining, as it turns out, through different autofluorescence channels, like in this case, DAPI and Texas red filters, native endogenous contrast of autofluorescence, soup of proteins at the diffraction limit, contain texture that let us stable and beautiful virtual H&E despite the autolysis artifacts of autopsy tissues. In a recent work, we've extended this to not just bright field virtual staining contrast, but also to polarization. This is actually a very exciting piece of work where we're taking autofluorescence of native label-free specimen, and at the output of the virtual staining network, we're giving you one stain and polarization channel of another microscopic contrast, which means you can do virtual birefringence imaging and virtual histology at the same time. In this application, we were looking into amyloid deposits. Amyloidosis is a major problem. The diagnosis of amyloidosis, unfortunately, is delayed several times, several years pass before a patient can be diagnosed, because most diagnosticians do not look for signatures of amyloid deposits within tissue. It's not as commonly diagnosed. And the ground truth for this is staining with Congo red, and then looking with after the bright field stain, looking with a polarization microscope to look for these birefringent signatures of amyloid deposits. Amyloid deposits, kind of like a crystal, although it doesn't have to be a crystal, they rotate the polarization state, and that's why a diagnostician manually needs to look under a polarization microscope to get these apple green birefringent signatures. We've shown that you don't need a polarization microscope, just like you don't need a bright field microscope, or just like you don't need staining. Label-free contrast gives you polarization contrast and bright field contrast of Congo red at the same time. The results were beautiful, showing you that you don't need a bright field scanner. You do not need a polarization scanner. You just need autofluorescence to get those signatures converted into bright field equivalent and polarization equivalent images, which would be very, very important for, I think, speeding up and making amyloidosis diagnosis better than what it is today. We need better technologies for looking into amyloid deposits in label-free specimens. So far, I've been obsessed with autofluorescence contrast. That's probably my favorite form of contrast for virtual staining, molecularly specific. All the digital scanners that are FDA cleared for digital pathology workflow, they have autofluorescence or fluorescence filters. So that's probably the strongest and the most preferred way of bringing contrast to label-free specimen or virtual staining. But that's not the only one. Earlier work from my lab utilized my second most favorite contrast mechanism. It's quantitative phase imaging, QPI, or holography, which means you're taking label-free specimen and looking into holographic microscopy to understand the phase delay of light through a process known as quantitative phase imaging. This function is a different function. It's equally peculiar and very, very difficult because holography is spatially and temporally coherent. Bright field is spatially and temporally incoherent microscopic modality. So we don't have this kind of a forward model to take incoherent fields or coherent fields and transform them to incoherent equivalents. And on top of that, of course, sample is going through a transformation from label-free to labeled. So these are really, really very difficult transformations to write a forward model for setting up an inverse imaging problem. And that's where supervised learning was very important and crucial, as I've emphasized a few times before. If you look at these holographic microscopy images, they're beautiful. They reveal the subcellular feature of the native tissue, but this time we're looking at phase signature, which means if you look at a detailed view of label-free specimen, now you're looking in a quantitative manner how every pixel was delaying light at this wavelength of illumination, which you can think of as another endogenous contrast. Refractive index, real part and imaginary part of the refractive index of a material is a fingerprint, and we're using those fingerprints to do virtual staining without label-free, without any labeling, using endogenous QPI signatures to do virtual staining. This is H&E of the skin tissue using phase stain. We call it phase stain because phase signatures of tissue is used here. And it also works for special stains like Jones Silver, Mason's trichome, and these are two different types of sample, kidney, liver, never seen before, showing you a good match to what comes out of histology. Again, this takes a technologist approximately 3 hours to stain. In a recent work, we also extended these ideas to another contrast mechanism, and that is reflectance confocal microscopy, RCM. RCM, reflectance confocal microscopy, is FDA cleared for dermatopathology use. This is actually an RCM device in a clinic being applied. It's non-destructive. You just gently touch the surface of the skin, and the diagnostician there is trying to understand, should I biopsy this or not? Should I biopsy this or not? And it's biopsy-free in vivo virtual histology this time because we take the RCM images coming from a volume with the grayscale contrast of reflectance confocal microscopy and convert them into H&E-like images giving diagnostician almost in real time virtual equivalent of a biopsy, layer by layer. This is showing you a movie of how it is working. This is the standard reflectance confocal microscope that is FDA cleared. We trained and tested new specimen, new patients using this device. And what you see here are images coming from the patient's skin, approximately 50 to 100 microns into skin. And every one of them is giving you the reflected light contrast with a confocal microscope that is this hardware here. And these are virtual staining results. This is a new patient never seen before, but the same device, meaning that that microscope was used in my training and testing. Now, I take this model that infers these beautiful H&E-like images and test the same model's transportability to another hardware. This is the handheld version of the reflectance confocal microscope. It's still a reflectance confocal microscope, but I've never seen this hardware before. And this is actually a new patient, a new hardware. Plug and play ready, it's actually starting to reveal virtual contrast, virtual H&E as a function of depth as the reflectance confocal microscope is scanning the patient's specimen. So this is a biopsy-free virtual histology in 3D coming from reflectance confocal microscope contrast that is FDA cleared, at least in the standard mode of operation. So I want to come back to this slide, which arguably is perhaps the biggest advantage of virtual staining among some others, which is preservation of tissue and multiplexing. But if I can take a single cross-section here and transform it into contrast 1, contrast 2, stain 3, stain 4, etc., I can also establish transformations between stains. You can take H&E and transform it into different stains. We call these stain-to-stain transformations enabled by label-free virtual staining. If you're too late, if there's an H&E in your data system, or if H&E comes routinely through a standard clinical workflow, and you're asking the question, oh, I love to see the H&E plus another contrast, another stain. That's where these kinds of stain-to-stain transformations will be transformative. A lot of times, because of insurance reasons, you start with H&E, and then special stains that are more expensive would come later. During this entire period, the patient would be waiting. What if you could provide a quick, distant H&E and virtually transform it to different stains that the diagnostician might need next week? That will be faster, more consistent diagnosis. This exact paper here demonstrated the utility of these stain-to-stain transformations, taking H&E images and converting them into special stains for improving the diagnostic accuracy of a group of board-certified pathologists for kidney disease. And that was essentially showing you the utility of these stain-to-stain transformations. To sum up, deep learning-based virtual tissue staining is saving labor and time. Some of these stains are really expensive and slow, including immunohistochemical staining, taking, for example, 24 hours. We preserve tissue, we can create multiplex staining, and we mitigate all kinds of variability in the staining quality among technicians. If you're interested, please ask me questions about hallucinations of virtual staining model. It's one of my favorite topics, but I'll leave that to Q&A and the discussion. But I want to say and emphasize here that this is not just an academic exercise that we've been enjoying ourselves for the last several years. This is also a commercialized venture. I started up Pictor Labs. I co-founded Pictor Labs as a spin-off from my lab in 2019. Pictor in Latin means painter, and we're painting the micro and nanostructure of tissue. That's how I was opening all the VC pitches during 2019 and 2020. So far, we've raised about $50 million to commercialize this, and we're in Santa Monica, approximately 30 people moving forward. Today's pathology is mostly glass-based. You can consider that as blockbuster. Every time the diagnostician wants to see a patient's specimen, there's a glass slide that you go to the store, so to speak, and take it, put it under a microscope, and inspect it. Very much like how we were used to watching movies with Blockbuster. Netflix changed the game. On demand, we can generate a panel of stains from the same cross-section that the diagnostician needs without going back to the store and exchanging, etc. Essentially what we want to achieve with digital pathology. This is actually a state-of-the-art model coming from Pictor Labs. It's going to show you multiplexing power, a whole slide image. You quickly bring in the H&E contrast. Diagnostician can zoom in and reveal different features. This is an excellent H&E stain. And then if you want, you can switch to an immunohistochemical stain. This is PEN-CK virtual staining on the same cross-section. And if you want a third channel later on, different parts of the tissue you can bring, in this case, for example, at the corner, you will bring virtually Mason's trichome virtual stain. Again, a beautiful stain revealed on top of each other. On-demand experience of virtual staining at different channels of information available. This is also my conflict of interest disclosure in the sense that I am a co-founder of Pictor Labs. So these were highlighting arguably the biggest impact that deep learning-based ideas had for cross-modality image transformations, approximating unknown functions that we did not know how to establish a forward model for. And this is where supervised learning shines. But despite its advantages of having an approach for unknown function approximation, there are a lot of problems with supervised learning. I didn't emphasize this a lot during my talk, but supervised learning for virtual staining is an expensive, tedious process. You need large amounts of high quality and diverse training samples, and you need domain expertise from pathologists to help us clean the garbage of histology. A lot of times, histology labs, when they send you the same image, claiming it's the ground truth, it's actually garbage, not usable. So you need to understand and clean those kinds of inaccurately sampled specimen, biopsy specimen. That's what we call pre-processing, and that's why we're better than the ground truth, because if you look at immunohistochemical staining, 30% of immunohistochemical staining fails. We do not have that failure rate because we filter them out. They don't contaminate our staining training process. Of course, there's also opaqueness of what is learned and potential hallucinations are concerned. So yes, this is the dirt bag of basically virtual staining through a supervised system. In general, these are problems with supervised learning. In the next several minutes, I'd like to pose a question. Hey, can we mitigate some of these limitations of supervised learning, although being very powerful, has some of these limitations? Can we use physics as a way to mitigate some of these limitations? For example, can physical laws serve as a regularizer for us? Can physics drive the learning process to regulate learning and regulate hallucinations to the physical boundaries of what we know? That's actually the story of Gedankennet. So Gedanken in German means thought. It's inspired by Einstein's Gedanken experiments, thought experiments. And here, I'm going to tell you the story of Gedankennet, which is a form of AI that lives in Jupiter. So Gedankennet is a form of AI that doesn't know anything about humans. It doesn't know if there's Earth or not. It doesn't know anything about microscopy, holography, quantitative phase imaging, or it doesn't have any experimental setup or samples to kind of image. It's completely living in a different world. However, it knows physics. Somehow it knows Maxwell's equations and the wave equation, because those are universal. The wave equation applies on Earth. It also applies in Jupiter, right? So it knows the wave equation, and this form of AI is tasked with a very challenging goal. We wanted to reconstruct holograms of samples, very much like what I've shown you with phase stain, with the quantitative phase imaging of label-free tissue. I want to reconstruct those holograms to reveal quantitative phase images. But GedankenNet will not have any experimental data, no experiments, no ground truth labels, no samples, no prior knowledge about samples, no optical hardware, no setup to train with. Only through thought experiments, Gedanken experiments, GedankenNet will teach itself in a self-supervised manner how to reconstruct holograms. Once it says, I'm ready, we're going to send it to Earth and give experimental results of holograms from real specimen. For the first time it touches on those holograms, we want it to be correct. Zero-shot learning, first time it should be successful on Earth. This form of learning is self-supervised learning through physics consistency. It's just the opposite of supervised learning in every single sense. And physical consistency or physics consistency is the driver here. So think of repeatability of physics. If I take, for example, an object and drop it to the floor and repeat this experiment twice, it repeats itself beautifully well. So this single observation of physics being repeatable is going to be the main aspect of learning for GedankenNet. So think of your favorite convolutional neural network or any architecture of learning engine here. That's going to be used for reconstruction of holograms. And GedankenNet, through thought experiments and physics consistency, is going to learn and engineer these coefficients here for performing zero-shot learning. Since it doesn't know anything about humans, human tissue samples, or anything about Earth, it's going to hallucinate random samples, just thought random samples generated. And without knowing what a wave is, optical wave is, it's going to be forming a complex valued optical wave. Now, the first experiment that it's going to do in a thought Gedanken manner is going to be this one. It's going to forward propagate using the wave equation, using Maxwell's equations that are universal. It's going to forward propagate the field that it hallucinated. Well, it forms, without knowing anything, some holograms that are to be reconstructed. Garbage in, garbage out. If you take some holograms that are coming from the wave equation of a hallucinated field, you will get some garbage out. Well, the second experiment is going to test physics consistency. If GedankenNet was correct, if I repeat the same experiment twice, just like dropping a piece of stone on the floor twice, it must repeat itself. If I do the wave propagation again, just like dropping the stone on the floor, whatever hologram I get through physics, wave equation, must physically be consistent with the original hologram, because physics is repeatable. The only loss here is self-consistency of the physics and the wave equation. So it does this hallucination and physics consistency checks thousands of times until it says, hey, I've learned, I'm done. GedankenNet is ready to be sent to Earth. Then after this learning through Gedanken thought experiments, we send GedankenNet to Earth and give for the first time holograms of different kinds of specimen, thin sections of specimen that are for the first time seen by GedankenNet. These are lung tissue specimen, Pap smear, Papa Nicolau smear for cervical cancer diagnosis, salivary gland, prostate thin sections. And it, for the first time, seeing these holograms created phase and amplitude reconstructions that are better than supervised learning, especially when you have a different types of specimen, different type of organ. Supervised learning models overfit to noise or fit to features of a specific type of object, and GedankenNet is completely immune to all of these overfitting because it was completely trained with physics consistency and physical laws apply across all types of tissue. So it's actually outperforming supervised learning. In fact, if you push GedankenNet to hallucinate, it doesn't hallucinate anything arbitrary. It hallucinates within the framework of physics, which means we gave GedankenNet purposely defocused holograms by several tens of microns. It gave us a certain reconstruction, which was not as good as shown with this correlation constant. But guess what? If you take this complex field that is coming from a defocused hologram and forward propagate it with the wave equation, it gives us the perfect reconstruction near. That's because this hallucination is not a hallucination, so to speak. It's actually completely following the wave equation, which means when it fails, it's actually failing within the domain of physics. It's giving you a physically consistent defocusing here because it was only trained with wave equation. And this way you can teach Gedankennet how to do autofocusing and phase rate reveal at the same time so that you can actually be immune to variations in the autofocusing distance or hologram recording distance. So it shows you the power of learning through physical or physics consistency laws. This is just the opposite to supervised learning. It's fast and cheap training, thought experiments. It doesn't require any experimental data hardware, no ground truth labels, no sample, no prior knowledge, no domain expertise, and zero-shot learning through a very powerful construct. Physics must be repeatable. And that's why if you know the physical laws very well, just like the wave equation or the Maxwell's equation, it's a good recipe for success. So in the interest of time, I'll finish off by saying that you can also flip the coin and look at the other side of the equation, where deep learning can help physics design these new optical systems beyond the solution space that we optical engineers are accustomed to seeing. And that's where deep learning helps us design better hardware, better structures. And in this domain, although I don't have time, I want to point you to some of our earlier work on deep learning design diffractive processes, where think of a black box where light matter interaction within that black box is shaped using deep learning, where in this case, optimization tool set of deep neural networks are helping us to engineer light matter interactions in unique ways that through intuition, through just physical understanding of the black box, we would not be able to solve. This is actually a beautiful framework for especially computational imaging. Think of a black box, which is very thin, maybe a few tens of wavelengths in thickness. Every layer of this is a transmissive element where at the diffraction limit of light, we're shaping the phase structure of these structured surfaces to work together. This is where deep learning is helping us to train in a computer the material, so to speak, so that once we're done, we can fabricate these diffractive layers, one layer following another layer following another layer, to solve a puzzle, to solve a problem using passive light matter interaction, which means in a few tens of picoseconds, you get your answer. For example, this is a diffractive processor that is working at terahertz waves, composed of approximately 200,000 trainable features engineered by deep learning. Every one of those small features here that look random, perturbation on the surface, it's actually a phase element that is engineered by deep learning. And this is an all-optical classifier, which means if you shine light here through a new handwritten digit, it will route the photons without digitizing anything in a few tens of picosecond to a detector that is pre-assigned to class 5. So which means it will do all optical classification as light matter interaction is happening through this thin optical volume, a few tens of lambda in thickness. And this means for amplitude encoded objects, we can do classification with just 10 detectors, the maximum detector score giving you classification. This is a never seen object before. This is a never seen number 94. Most of the photons went to this detector, correctly classifying it all optically. It also works for more exotic objects. And one thing that I want to mention here is that you can also use phase encoding because these are coherent processors, which means the information at the input can be phase encoded. These are fashion products that we learned how to classify by encoding them in the phase channel. For example, this is a dress never seen before, phase encoded. Most of the photons at the back focal plane of a diffractive processor went to this detector, which was pre-assigned to dresses, so on and so forth.
In general, this is the framework for visual computing. Do not confuse it with integrated photonics-based designs, because these do not need any pre-processing of information. Whatever aperture you give us, the phase information, amplitude information, polarization information, and spectrum information within that input aperture can be directly accessed and processed within a few picoseconds or tens of picoseconds, depending on the wavelength of interest. They can be directly processed with these passive light matter interactions. We've been playing with this platform for various different applications, all the way from single pixel sensors to quantitative phase imaging, designing different kinds of imaging systems that can, for example, see through random diffusers. So think of, for example, a random object, unknown, constantly changing, a random diffuser in front of it, completely blocking it, also constantly changing. And the diffractive processor here is a piece of passive material that is solving this inverse problem all optically in tens of picoseconds. It reveals the image here as the light is diffracted through these kinds of structured volumes. We can also use additive manufacturing to fabricate these at the nanoscale to bring the operational wavelength to infrared and even visible wavelengths. And finally, this is my last slide. There's also a beautiful push-pull between diffractive processors and digital processors, especially digital neural networks, because I believe diffractive processors and convolutional neural networks specifically form a beautiful language through programmed diffraction. So this is where we see a lot of exciting opportunities by programming like diffraction for digital world to better harness the power of light and the degrees of freedom that we have. So deep learning and optics and photonics have a very exciting intersection set where we can enrich our designs and perform transformations, at least at the microscale and nanoscale, that were not possible before. And with this, I'd like to conclude and acknowledge all of our funding agencies and students and postdocs behind this work. Thank you very much for having me.
Okay, thank you very much, Professor Ozcan, for the wonderful talk. We have a few minutes, but let's open the floor to questions from the audience first. Anybody from the audience having questions? Feel free to ask.
So I would like to begin with the prompted question. With this level of generalization, as you showed in the first part of your talk, hallucinations must have happened. So before you got to your wonderful Gedanken technology, how did you control hallucination in the systems you built before that? I'm very interested to know, while maintaining a very high level of generalization.
So for tissue staining, there are basically two different types of hallucination. One type of hallucination is artifacts, generation of artifacts that a diagnostician can easily understand. And those kinds of artifacts routinely happen today in digital pathology workflow. For example, this is a tissue specimen that is folded. You see this region, it's tissue folding on itself. This is virtually stained, and it still works, but the accuracy here of our inference is not reliable because we've never seen a folded tissue. And guess what? Diagnosticians don't care about these kinds of features, and they move away. And also, guess what? This happens routinely in traditional histology. So they know how to deal with this, they ignore it. So these types of hallucinations are not concerns, and they happen, they will happen. Another form of cute, I would call, type of hallucination that is not a concern is some sort of out of distribution hallucination because of maybe some changes in autofluorescence. This is Mason's trichome tissue that we virtually stain. Hey, guess what? We have here green color, right? Mason's trichome doesn't have green color. We were puzzled. Why are we, having this out of distribution staining here? Once you look at the fluorescence, autofluorescence channels, you see here actually there is a dust particle, perhaps a microplastic, that landed on that tissue that was giving you a huge autofluorescence signature. That's not tissue, that's something else there. And then we were hallucinating there. And in the chemical staining, there was nothing like that. It was washed away. Again, this type of hallucination, let there be these types of hallucinations. We don't care about them. They will happen. And it's not a concern because these kinds of artifacts in different domains happen through the chemical workflow. And diagnosticians, pathologists will ignore them. They will say, I'll look at other parts of the tissue, just like what they do today. The most dangerous form of hallucination that we are working on is hallucinations where you imagine a new patient that never existed. Think of, for example, a cancer patient with cancer-related, enlargement of nuclei, etc. Rather than stating it like that, generative AI can be actually creating a benign region of the same tissue, stain it perfectly without any artifacts, and the diagnostician is ready to write a report. Those are realistic hallucinations, and this is an unrealistic hallucination. No worries about these kinds of hallucinations, but realistic hallucinations are the most dangerous ones. And we have shown that there are ways to handle realistic hallucinations through the physics of autofluorescence and virtual staining. So to better understand if a virtually stained image is containing realistic hallucinations that diagnosticians do not understand or cannot understand, we're also looking at the power of some physics-based inference to help us understand how compatible your virtual staining result is with respect to the autofluorescence physics. And that's something that diagnosticians cannot do. It's beyond their understanding. But you can teach another network, look into what we call physics consistency again, although not shown here. And that's essentially helping us mitigate the second class of realistic hallucinations that, in my opinion, form the most dangerous form of hallucination because they create new patients never existed before.
Very interesting answer. I wondered, because Maxwell equations are at such a basic level of physics, what is the usage of resources like GPUs and memory when you are really emulating physics at that lower level? Are you operating in some domain other than time and space? Are you, for example, operating in a transform domain? Could you comment on the structure of these physics-based networks a little bit, at least?
Yeah, so the Gedankennet framework inference is very fast. So you're looking at maybe a sub-second per millimeter square. So in other words, if I go back to Gedankennet here. So this box here is composed of Fourier transform modules that are learned. So that's why it has two distinct types of neural networks put together. One of them is operating in the Fourier domain. The other one is operating in the space domain. So this has modules that are learnable filters in the spatial frequency domain and space domain directly. That's why it has two different loss functions to check the physics consistency. Once this is trained, for a given millimeter square field of view of a specimen that I want to construct, let's say a millimeter by a millimeter tissue sample, it will be approximately a second or so, depending on the GPU that you have. But these are typically, game consoles like $10,000, maybe $15,000 GPUs that we use. In terms of the Maxwell's equations, in other words, in terms of checking the ground truth, like, I need to understand what I'm imaging to see if I'm successful or not. So that's where I'm using, just to understand the success, not to train anything, just to understand the success. I'm using, of course, solutions to the wave equation. There, I'm using not the Maxwell's equations directly, but I'm using the wave equation, scalar wave equation, that's a derived quantity from the first two Maxwell's equations. So basically, if you combine the first two Maxwell's equations, you can write the wave equation. And wave equation solutions are fairly simple and standard in terms of how physically we take, for example, a hologram and do phase retrieval. They take a while to convert because they're mostly iterative. They're guessing a phase, and based on the wave equation, scalar wave equation, they're kind of propagating it and correcting their guesses. So although the ground truth takes me maybe 10 times to 100 times more time per millimeter square to generate, but that is fully physics compatible because they are driven from the Maxwell's equation through the wave equation. And since I do that only once to see the ultimate ground truth for my comparison only, it doesn't constitute a challenge for our learning, or it doesn't constitute a challenge for even our comparisons.
Thank you.
All right, thanks, Pankaj. Any other question? We are approaching the time, but you know, probably I can ask the last question here. Very exciting, you know, technology for this digital pathology paradigm. I think, in your opinion, what's the future of this digital pathology? I think you showed this picture lab where, you know, we are transforming from this old blockbuster style into this Netflix, you know, demand-based one. You know, I still, you know, curious to see, you know, the how to say this, the penetration of this digital pathology technology. I do see there's a huge benefits for doctors because they save time, you know, but you know, is there any possibility that this technology can be approachable by, you know, patients for general consumers, right? Because, for example, you know, like what we would have been doing in mobile health for decades, where we wanted to bring closer these on-site diagnosis tools on your consumer-based smartphones, where you can test something. So in your opinion, is that far, or we are almost there?
So I think the first castle to conquer is digital pathology. So a lot of hospitals are still based on glass. They don't have a digital pathology infrastructure. Some in the United States and globally, several hospitals are still storing glass and not digitizing their image, which means if the diagnostician needs to see a patient specimen, they take the glass, just like we took CDs, DVDs, and put it under a microscope. So first application for virtual staining technology using AI is to convert all forms of pathology from glass to digital domain. This requires some, of course, capital investment. You need digital scanners, you need a data security infrastructure, cloud-based infrastructure, and all of that. And that can cost you millions of dollars for a hospital to convert from glass-based pathology to digital pathology. But now that we have virtual staining technology, we believe the return on investment for converting your glass-based pathology to digital workflow will be tremendous. From the perspective of eliminating some of the FTE, so the full-time equivalent jobs that you need for histotechnologists to stain, so that you can handle larger volumes with a smaller size, eliminate the cost of toxic chemicals involved in histochemical staining, and providing diagnosticians rapid multiplex stains so that the diagnostician can sign off at a case of a patient faster, more accurate. It's a win for the hospital healthcare system. It's a win for the diagnostician. They get faster access to higher quality content to make their diagnosis accurate. It's also a win for the patient and insurance companies because unnecessary hospitalizations, delayed treatments, inaccurate treatments, secondary biopsy, bringing the patient back again for a secondary biopsy. Lots of back and forth between the diagnostician histology lab with more specialized stains, IHCs, the chemical stains of different kinds. They will be eliminated. That means there's a lot of incentive right now for virtual staining to kind of convert glass-based pathology to digital workflow. And I believe that's going to be the most important battle to win first before we see applications of virtual staining come closer to the patients, maybe through small clinics, point of care offices, stuff like that. At some point, it will. But that's actually perhaps in the triangle or pyramid of opportunities, it's a little bit higher up. It remains to be successful. It waits for the success of virtual staining deployment in hospitals and being part of a vital and necessary and essential part of the digital pathology workflow.
Yeah, I can definitely imagine that maybe in the future, like the patient can access to its stain, like virtual stain via a phone app, right? With the diagnosis results or reports. So he or she can
Perhaps. Yeah, perhaps. So I mean, those are not impossible to achieve with some smart hardware. To a cell phone, you can imagine some sort of autofluorescence images. Maybe it will give diagnosticians additional information, but this is really something that is a little bit far in the future than what I'm sharing here in terms of digital pathology workflow.
Yeah, but I think if it happens, like it'll be huge benefit for potentially all the hospitals, right? Across the world. Yeah.
That's true.
Okay, we are kind of way out of time. So, but thanks again, Dr. Ozcan, for the wonderful talk. We really appreciate the time and the wonderful sharing of your amazing research. Thank you very much.
Thanks for having me. Thanks for having me.
Thanks so much. Thanks everybody. I'll see you guys next time then. Thank you. Yeah, bye.